I'll just share my screen.
All working well, Lee.
Good, good, good. Just arranging my other screen. Excuse me a second. Right. Okay, so welcome to everyone. Well, vision and colour is a huge topic and can become intensely technical, but this talk is an overview, and we're trying to keep it as comprehensible as possible. It's in part educational, and excuse the pun, it's a bit of an eye-opener, part entertaining, but I want to show just how easily we can be fooled, and it's quite shocking to see that how little of what we see actually reflects what's really out there. So hopefully at the end of this you'll be convinced. Okay, so the white light from our sun can be split, as we know, using a prism or a diffraction grating into a rainbow of colours, and the light waves are refracted and bent as they go into the prism and leave the prism, and that separates the colours. The shorter the wavelength, the more the light is refracted, and this is technically called dispersion. But if you take, or as Isaac Newton did, he took one distinct colour and put it through a second prism and found that it couldn't be split. Now these days, using modern prisms and diffraction gratings, we can split light into individual wavelengths or frequencies. Now the primary colours of light for human vision are red, green and blue, and mixing all three, you can see in the centre there, makes white, and blue and green give cyan, red and green give yellow, and red and blue give magenta. It's called additive colour mixing, but magenta is a figment of our imagination. So there is no frequency for magenta, there's no wavelength for magenta. It's the way we perceive it. Okay, now if we look at the overall spectrum of all of the, because light is just electromagnetic radiation, and if we look at the full spectrum all the way from radio waves all the way through to gamma rays, we're only seeing a very tiny section of what's actually out there, and we see less than 1/1,000,000th of actually the full spectrum. Some snakes can sense infrared, and honeybees and some birds can see ultraviolet. Okay, so the primary colours of printing are yellow, cyan and magenta, and again mixing all three makes black, but not a very good black, and also you're wasting colour ink. Some cyan and magenta give blue, magenta and yellow give red, yellow and cyan give green, and this is called subtractive colour mixing. And colour printers also have blacking, mainly because you get a deeper black and it avoids wasting coloured inks. And so it's called CMYK, and the K stands for key black. So when light strikes an object, the colour we see is the light that's not absorbed. In other words, the light that's reflected off the surface, and all the other colours have been absorbed by that surface. Okay, so a green object absorbs all the colours from the light except for green, and a white object absorbs very, very little and reflects most of it into our eyes, and black objects absorb most of the light falling onto them, and so they're quite often hard to pick out detail unless the illumination is extremely good. And the retina at the back of our eyes, a complex collection of cells, and its job is to turn light into signals that our brain can understand and interpret. And the light, it's only the retina is actually light sensitive, and it's roughly the area of a 10p coin, and it's packed with photosensitive cells. But because the lens in the eye, which focuses the light, is curved, it bends the light, it actually creates the image on the back of our eye upside down. And the brain turns it the right way up. And also it combines the image from two eyes into a single image. And having two eyes also gives us binocular vision, so we can perceive depth. Now, some people can't. If you've had an eye that wasn't properly aligned, you may have had it corrected later in life, you probably find your binocular vision is either impaired or not there at all. So let's look at the eye. Now, we're very sensitive to low light levels, and that's because of a special type of cell shown here at the top called a rod cell, and they have a substance in them called rhodopsin, or visual purple, as it's sometimes called. And we see colors because of 3 different types of cone cells. So they're sensitive to primarily red, green, and blue, and that's because those cells have a particular substance in them called photopsin, and there's types 1, 2, and 3, which give us the sensitivities to different wavelengths of light. Some very lucky people, mainly women, 12% thereabouts, have an extra cone cell, and they can see somewhere between red and green, allowing them to pick out different hues with much more acuity. In darkness, the cone cells don't function at all. It's the rod cells that are giving us our night vision. And the color we see is a product of the illuminating light and the eye's combined response and our brain's interpretation of that. So color is a psychophysical property. It's our perception. It's not reality. So most people with normal vision can distinguish over 10 million individual colors. So when some scientists, only a few years ago, about 20 years ago, were studying the response of mice that had a retinal disease, where they no rods and cone cells left, they found that their body clocks were still working perfectly fine. And it led to the discovery of a previously unknown receptor cell in the eye containing a substance called melanopsin. And that is found in these things called intrinsically photosensitive retinal ganglion cells. Scientists love to give things complicated names. Anyway, these cells, they're nerve cells, and this picture on the top right here is a retina that's been opened out and stained so you can see the melanopsin. And so you can see it's mainly centered in the middle here, but there are blue dots all over the place. And so it's particularly sensitive to blue light, and it affects the center in the brain, which is where our body clock is located. So these cells govern everything from pupil size to our sleep-wake cycle, the levels of arousal and our attention. So the rod cells give us our night vision, but they cannot distinguish color. And this is a plot here of the overall sensitivity of our eyes. And it's the cone cells located in the center of the retina, an area called the macula, which you've probably heard of in macular degeneration. But the cone cells are sensitive to color, but not very good at night. Okay, so they're sensitive to a range of wavelengths, but our eyes are most sensitive in the green region of the spectrum. Okay, and all the other colors we see result from the stimulation of these cone cells. Okay, this is probably what you would expect to see, but we don't. We see a very, very wide range because the cone cells are stimulated. There's overlap, as you'll see in a minute. So the response here is plotted. So the S cells are short wavelength cells, cone cells. This is the response, and then you can see the medium ones and the long wave ones. And there's no cone cell for yellow. So that's brought about by a combination of the green and red cones working together. Now, this is where it gets quite interesting because there's a very small part of the macula called the fovea, and I'm just trying to indicate it here. in the center of the macula, and it's only about 1.5 millimeters wide, and it's where most of the cone cells are located. It represents less than 1% of the size of the overall size of the retina, and it's located in the center of the macula, and that's responsible for our sharp central vision. And it's the area where fine detail can be distinguished. And in that area, there are 150,000 cone cells per square millimeter. So it's really packed with cone cells. And it's surrounded by a larger peripheral area, which gives information of low resolution. And approximately half the nerve fibers that go to the brain are connected to the fovea. So they carry 50% of the information and takes up 50% of the visual cortex in the brain to process information just coming from the fovea, this tiny little spot. Hawks, swallows, hummingbirds have a double fovea, and that enables them to track movement much better. So let's look at the brain. Now, the color processing begins at a very early level in the visual cortex. And there's this ventral stream, this purple area indicated here, is very important for object and color recognition. And the green area, the dorsal stream, is mainly focused on position in space and motion. And they originate from the visual cortex. So color perception in humans is not a property of electromagnetic radiation. It's visual perception by the observer. Okay, so do you see your nose? If you think about it, you probably say, well, yes, I can see my nose, but most of the time you don't. Your brain doesn't care about it, so it edits it out. And the same if you wear glasses, you're not conscious of the rim of your glasses all the time. Your brain just edits that out. It's not of interest. And we have a blind spot in our eyes, and that's where all the blood vessels converge and where the optic nerve comes in and out of the eye, and it's indicated here. And if you want, you can find your blind spot. Here's a thing to do. Hold your thumb out and close one eye and look at your thumb. Right now, keep your eye absolutely steady, and then move your thumb without moving your eye. Move your thumb to the right or the left, and keep your eye focused on that same spot at dead ahead. And all of a sudden, you'll see the top of your thumb disappear. But that's in your peripheral vision. But that's how you find your blind spot. Okay, so there are no light sensitive cells in that region, and it's about 3 o'clock in your right eye and 9 o'clock in your left eye. And again, you don't see an empty spot in your vision because your brain literally invents stuff based on what's nearest to it. Okay, so we think we see the whole world, but we're looking through a tiny visual portal most of the time, about the size of both of your thumbnails when held at full arm's length. Okay, and you have to move your eyes when you're reading, of course, because most of the rest of the page is blurry. And those eye movements are called saccades, and we don't see them. We don't see that movement because they're edited out. So when our eyes are constantly darting around, we don't see those movements. So we should see a blank or a blur, but the brain just edits it out. And I'm going to illustrate this. I'm sorry this is going to contain some flashing images, but have a look at this scene, and there are going to be some objects which are going to be appearing and disappearing. See if you can figure out what is appearing and disappearing. Okay, well, many of you may have seen this, the lawn, the item in the lawn here that was disappearing, this flower bed. And there's a big planter here on the right-hand side, which was coming and going. But I'll bet most of you didn't see this, the tree that's here in the image. I'll see if I can show you that. There you go. So that tree was being added and removed. And you probably didn't even see that. It just shows you that at any one time, your eyes are focused on a very small spot. Okay, so why do we need to see in color? Well, it gives us low level image processing for finding things. It allows us to segment images and find boundaries. So it makes things pop out in a visual search. It groups up, it helps us group items together. It gives us the ability to recognize objects, identify materials, object recognition, classifying objects, categorization, memorization, and emotion, social, sexual signaling as well in animals particularly. Now look at this picture here, and you can clearly see a nice fruit stall here with various different types of apples and some oranges and so on, some other fruits, some pears down here, melons. Quite easy to pick everything out, isn't it? Now pick out the different fruits. When now I've taken the color away, it's much more difficult. So finding the different fruits and finding the boundaries between the different fruits is quite difficult. And if I put the chromatin and chromatic information in, you can see all the boundaries. Here's a black and white version of a jungle scene. Now it's really important that you be able to pick out the items in that scene. Now there's a predator that's waiting to jump out at you. And if you don't find it within a second, you're his lunch. Can anyone see it? So why is it so difficult to find? Well, because all you're doing, you're seeing light, the amount of light that's reflected from surfaces, you can't pick out detail. And there he is, the panther waiting to have you for lunch. And as soon as you put the color in, you can see all the detail. You can see the trunk, the tree, you can see the panther, and so on. Okay, so the image shows the surfaces according to the quality of light they reflect, not just the intensity of light. And your brain has got much more information to go on for making decisions. And so we can see a greater number of similarities and differences between different objects, and absolutely vital for survival. Okay, now what's amazing about what you've just done very easily, it's incredibly difficult for computers to do the same thing. They're getting better at it, but they're still not very good. Okay, so what's color blindness or color deficiency is a common thing. It's an inherited condition, typically affects many more males than females, and it's an 8% of males and less than 0.5% of females have some issues with color vision. And red-green color blindness is the most common, and it's due to the lack of one or more types of color cells or cone cells in the retina. And it's typically a defect on the X chromosome. And women have 2 X chromosomes and men only have 1. So that's why more men are affected. And if we look at this picture, the upper items here, the cap, the t-shirt and the sneakers, and then look at, this is a simulation of what they would look like if you had red-green color blindness. So very difficult to distinguish. So there's also blue-yellow color blindness, which is very rare, and total color blindness, which is even rarer. And here we go. These are the things that medics and opticians use to check color blindness. And these circles here, these spots have numbers on them. And I find that the one on the bottom right here most difficult to see. I can see it, but it's the most difficult, I find. Put you out your misery, those are the numbers. And they're called Ishihara color vision deficiency test charts. Okay, now in the animal kingdom, some animals only have literally one type of cone cell. Some have two. We have three. And then some have four and more. I'll show you a couple of creatures later that have unbelievable vision. So birds have an extra cone so they can see out into the UV. Dogs only have two, so this is typically what they see. They don't see reds and greens that well. And we humans, most of us anyway, have three types of cones, and as I say, some lucky people have four. So this is common blue bottle butterfly, has 15 distinct sensitivities, spectral sensitivities. And this mantis shrimp has between 12 and 16. They're still investigating this creature. And you would think that underwater, being able to see in something like UV wouldn't be particularly good because water absorbs most UV. But they reckon that the receptors are actually mainly orientated with detecting polarization of light, a bit like Polaroid sunglasses. Okay, so a very few people have a thing called synesthesia, where there's a cross connection in the cognitive pathways in the brain. And when they see colors, they have other related sensory experiences. So, and synesthesia does vary from person to person. And so a common form is called grapheme color synesthesia, and letters and numbers are always inherently colored, and the same letter always has the same perception of color for that individual. And you can even have tastes and textures associated with colors too. So when we're talking about color, we're actually technically, and this is human classification. This is this is purely how humans have classified colors. We're typically talking about hue. Okay, and obviously you've got strikingly different hues here. Okay, so we're talking about hue, and you can have a constant hue but different colors because they're different amounts of white and dark in the color. Okay, and then there's a thing called chromaticity or chroma, and that's how strikingly vivid or bright the color is. Okay, and if low chroma or no chroma, achromatic, there's no color, it's just black and white. And it's often confused with saturation. So these colors here are constant chroma, constant intensity. Okay, and then you've got saturation, and that tells us how a color looks typically under different lighting conditions. So a room painted a solid color will vary over the day as the lighting in that room changes. Okay, sometimes called intensity. So think about it in terms of pale or weak or pure and strong. And then there's a thing called luminance or value, color value. And you're looking at the light or dark, brightness. And if you look at these colors here, canary yellow is higher, if you like, than the blue-black color in terms of luminance. And then we've got tint, shades, and tones. So this is how the color varies from its original hue. So if you add white to colors, you get tints. And if you make it darker by adding black, you get shades. And if you add gray, then you get tones. And again, this is all how humans manage and classify colors. Now, on color and TV and film, you may see in the credits somebody attributed to be the colorist. Now, what do colorists do? Well, they ensure that all the shots in each scene match one another in terms of the balancing the color saturation and luminance from shot to shot to give consistency. So they correct the color differences throughout the whole program. Color displays, well, we use the three primary colors on color displays on TVs, on smartphones, computer monitors, and they're made up of red, green, and blue picture elements or pixels. And these different pixels are driven electrically, either harder or less hard, to form a whole spectrum of different colors. And of course, they're very, very tiny. And it relies on additive color mixing of light. Now, you may have heard of color temperature associated with different forms of lighting. I'm not going to dwell on this, but because it's really it's not strictly speaking color, and it's mainly used in things like photography, in lighting, videography, and so on. Now, if talking about lighting, these are the different types of the spectral properties of different types of illumination that we use in our homes. So daylight has got this typical spectrum in terms of intensity, incandescent light, and then fluorescence, very spiky and peaky, and halogen is very similar to incandescent. And then the two main forms of LED have different spectral properties to get warm white or cool white. So if you want to measure color accurately, it's called colorimetry. And you can use spectrophotometers to analyze light, break it down into its individual wavelengths and measure the energy at individual wavelengths. So our eye perceives only a single color for any given energy distribution. So we have to express color measurements in a perception related way. And so there are many different systems for measuring color and representing colors. This is one specific one based on RGB measurements on an axis. It's called a tri-stimulus system, and basically you measure X, Y, and Z proportions. So X, Y, and Z. And it's also used. You can use absorbance of light to measure the color, measured with a spectrophotometer, typically done in laboratories. Now, when you look at colors, borders and framing make a huge difference to the perception. If you look at the image on the left here, it's very, very much more. It pops, as the Americans call it. The colors seem to stand out much more dramatically if you put borders. And of course, this is the principle behind stained glass windows. Mixing different colors in color printing gives us a whole range of different colors. Lets printers produce any color they want. And but as I say, mixing all the colors will give you black, but not a very good one. And again, that relies on subtractive color mixing. Okay, now art, obviously much art depends on things like coloured pigments, and most of them certainly traditionally came from natural sources. So iron oxide was one of the very, very earliest. That goes back now to over 80,000 years in human history. And you get a range of colours with iron oxide: yellow, orange, red and black. Black, though, is typically we obtain from wood charcoal. We've had vermilion from mercury, from cinnabar. I mean, obviously, some of these substances now are no longer used because they're considered dangerous. And ultramarine came from a semi-precious stone called lapis lazuli. And that was very highly praised by artists in the early days. So minerals can have a wide range of different colours due to trace impurities in the crystal lattice. And it doesn't take very much impurity to give a distinct colour. So ruby, for example, is pink. It's a coloured form of corundum, which is aluminium oxide. You can have different types of corundum, which are different colours, and they're called sapphires. So the colour of ruby is due to the element chromium, traces of chromium within the crystal lattice. You can get things called pleochroic minerals, which change the colour depending on the angle that you view them at, and also the light source that's used. So this one called corundum here is shown in normal light and in polarized light, and it looks very much darker in polarized light. And then again, there are other minerals that do this. And then we get, traditionally got a lot of pigments in the past from natural sources. So we get indigo from woad, and even from insects. So the cochineal beetle, we get carmine red. So you put your red food dye in when you're making your cake, and you put in squeezed, crushed up beetles. But it's an unusual pigment because it's actually transparent. And then we invented coloured dyes, mainly because of the coal tar industry. A whole range of different coloured dyes, and then chemists set about synthesizing even more different coloured dyes. And then we've got things called lake pigments. So this is called madder lake, which is made by taking an organic dye, and then you put it with a binder called a mordant, typically a metallic salt, and you get these lake pigments. Now, these are a type of colour which is called fugitive, which means they change with time, typically as a response to light. So typically they fade. So in painting, there's no limit to the number of colours that you can have in your palette. But many, again, do come from pigments. And a famous painter called George Seurat was one of the first artists to experiment with composing pictures from just tiny, tiny, specifically coloured dots. So this picture here is called Sunday on Le Grand Jatte. And what he did was, it was a huge canvas, 3 meters by 2 meters. And when you look at it, you blow this section up here, you see it's just made up of coloured dots, little coloured squares. But viewed from a distance, we see an even distribution of colour. So other sources of colour in nature, iridescence is one. So this is where a surface absorbs light and then re-emits it, but at a different wavelength, and it can change with the angle of viewing or the angle of illumination. So we're all familiar with this in soap bubbles, feathers, butterfly wings, inner surface of certain seashells, and certain minerals. And it's created by it's called structural coloration. And it's because the the surface causes interference effects with light. So oil and water, seashells, the peacock feathers, there are no pigments there, that's all iridescence. Certain beetles. Now pearlescence is another source of colour. That's mainly due when the reflected light is predominantly white. So we can now get pearlescent paint finishes on cars, on smartphones. And of course it occurs in nature in pearls and mother of pearl. Fluorescence is another source of colour. So this is where emission, again, a surface has absorbed some light and re-emits it in a shifted wavelength. Typically, it's more striking when ultraviolet light hits the surface, then it's re-emitted at visible light, giving the corresponding colours. So we look at this mineral, for example, this mineral called calcite. On the left-hand side, that's just in daylight. On the right-hand side, in strong UV, you get all of these different colours coming out because of fluorescence. Okay, and fluorescence occurs in nature too. So jellyfish and quite a variety of different marine animals and fish. And we exploit fluorescence well, we have done in things like nightclubs. We're using black light. So this high vis gear here takes in light and re-emits it, predominantly UV light, re-emits it, so the high vis clothing stands out. Okay, so I want to show you now, focus on how our visual system is very, very easily fooled. I'm not going to go through this in great detail, but if you stare at this black cross on this yellow area for a while, and then you move, after 30 seconds, you move your vision here to this black field, what you'll see is an impossible color called Stygian blue. And similarly, there's a self-luminous red and a hyperbolic orange. And these colors are not real, they're after images in our eyes. Now, I want you to count the white dots. Do they keep going black? Now then, this is not a trick. The lady there's picking up that square and moving it, and all of a sudden we see it change. The reason for this is our eyes see that square there in shadow, and we're familiar with this pattern, and so we automatically make a compensation in our brains and assume that that square must be lighter than it really is. As I say, this isn't a trick, this is a genuine person moving a tile. Now then, if I told you that these two squares here, these two shapes were the same color, you wouldn't believe me. The background makes a huge difference. Now, all I'm going to do is put a black shape in over the join between the two surfaces. And if you let your eyes accommodate a little bit, you'll see that the colors all of a sudden go a whole lot closer together. And that's all I've done. I've just put a black rectangle over the join between the two. And what's affecting you there is the background and the illumination. And again, this is not a trick. This is down to illumination and our brain making compensatory adjustments. Those two squares in the cube are the same color. I'll show it you again. So this square here and this one here are actually the same color. So our brain makes adjustments. Sorry. Right, and then of course, a few years ago, I think it was 2015, there was this sensation on the internet. Everybody's talking about this dress, and people were arguing over what color it was. Some people saw it as blue and black, and other people saw it as white and gold. And you could have two people in the same room looking at this dress, and they would argue about what color it was. And again, this is due to a thing called color constancy in our brain, where our brain makes compensatory adjustments to what we see depending on the illumination. And so some scientists literally got groups of people, they got an example of this particular dress, put it in a tent, invited people to walk through the tent and have a look at it. And then on the way out, they asked them what color they saw. And 50% of the people saw blue, black, and 50% saw white and gold. So it's due to a thing called color constancy, and it's an effect in our brain where we make adjustments. Now stare at the cross, and what do you see? Okay, so you see a gap appearing in the lilac discs. Okay, and then you see a green disc apparently running around the circle, but there's no green disc. That's an after image in your eyes based on a thing called visual fatigue. Now, which way is the ballerina spinning? If you move your eyes from left to right across, you'll see a change. And the reason for this is this image has got very little information in it about the depth. And so that's why it flicks, that's why it changes from one way to the next. Okay, how many prongs are there? Now, again, this is not a trick. These lines are all horizontal perfectly and perfectly parallel. There's no sloping lines in this image. I'll show you if you look at this distance here, and it's the same there, it's the same there, it's the same there, absolutely the same. Look at the blue strip, look at the distances, they're absolutely the same. There's no sloping lines in that image. Okay, which circle is bigger? The orange circle, which is bigger? They're identical. Of course, the one on the right looks bigger. The two yellow lines, the one in the distance looks much bigger, but it's not, it's the same size as the lower one. And that's because of the train tracks and our idea of distance. And because it's in the distance or appears to be in the distance, therefore it must be bigger. And that's our perception again. Now this is an interesting one. This is called perspective or an anamorphic image. Now the chap here has painted this or drawn it on the pavement using coloured chalks, and in order to get the lady's leg sticking out, apparently sticking out the water like that, this is what he had to do. So when you see it from that other perspective, from that other angle, walking this way, you see that. But in order to get that illusion on a flat surface, he had to draw it like that. So it's anamorphic projection. I'll show you another one now as well. Now this one's got a little trick at the end just to as a bit of a joke, but again, it's exactly the same. It's an anamorphic projection of a polar bear. And notice that polar bear is drawn on the road, and then it goes up the curb and onto the pavement. A bit of a clever video editing there. Okay, and again, this is perspective illusion, and it's not a trick. I do assure you, it's not a trick. These two shapes remain identical in size. But our brain is making compensatory adjustments. Again, is this face sticking out, or is it concave or convex? Our brain is so determined to see a face that even when we're looking at the concave side, it still projects out. Okay, have a look at this image. This is called autokinetic. There's nothing moving in that image. Everything's completely static, but if you move your eyes around across the image, you'll see things sort of twirling or moving. Okay, so it's a completely static image. But about 5% of people can't see that. They're just not, they don't see the illusion. Okay, count the triangles. There aren't any. Our brain is connecting the dots, interpreting what we're seeing. And we see triangles, but there aren't any triangles. So we're doing pattern recognition. We're seeing what we expect to see. And again, things like this, this is exactly the same color, yellow, but on different backgrounds, and it makes a huge difference to how clearly and how distinctly we see it. Same yellow square on different colored backgrounds, and they appear quite distinctly different. Especially, I find the one on the white background really quite hard to look at. So sometimes, and especially in modern science, we use false colors to enable us to see things. So this is a picture taken in multiple wavelengths, many of which we can't see through with our eyes, of galaxy M82, and it's been taken in X-ray, which is represented in blue, in infrared, which is represented in the red, and it's also visible light, which is shown in yellow-green. So this is a composite from 3 different telescopes: Hubble telescope, Chandra X-ray telescope, and the Spitzer infrared telescope. But the different wavelengths are represented in different colors, so we can see a composite image, because we can't see infrared and we can't see X-ray. We use false colors to help us detect things like infrared. So you can see the steam train on the left-hand side, and the whiter bits are the hottest bits, the orange bits are not so hot, and the red bits are the cooler areas. And if you look at the house on the right hand side, this house here, this house is what they call a passive house, built to a very high standard of insulation, and there's very little heat leaking from this house. But if you look at the house in the background behind the trees, you can see that's leaking a lot of heat. Okay, so the false colors are used to show us different intensities of infrared radiation. Colors affect our mood, so this has been studied extensively over the years. A German polymath called Johann Wolfgang von Goethe wrote a monumental tome in 1810, 1,400 pages in 3 volumes, all about color, every aspect of color. A lot of it was wrong, technically, these days, but it shows that people have been very, very taken by color, very keen to describe it, to investigate it, because it really does affect our lives so much. And then we put things together, we call them complementary colors. So if you're mixing pigments, this is a color wheel. There are loads of different color wheels around, but it's just to try and represent which colors go and which colors don't. And if you're mixing light, this is a color wheel that corresponds to complementary colors. And then we get, of course, colors in fireworks are often amazing. That depends on chemistry. So we've got strontium salts give us red, calcium salts give us orange, yellow, sodium, barium gives green, copper gives blues. Combine copper and strontium and you get purple. And if you want silver sparkles or things like that, you can use magnesium or aluminium. And if you want really burning metal effects, then magnesium, aluminium, titanium in various combinations. So, in summary, this is just introduced the subject of colour and how our visual system works and how we perceive colour. But it is a very, very complex subject when you really delve into it. So our perception of colour is very, very strongly influenced by and adjusted by our brain. But the colours play a vital role in life, and they affect us far more than we give credit for. They can alter our mood and they influence our choices. Sight and colour perception is probably, humans anyway, our most important sense. But many animals, smell is more important. So vision comes second. They help us stay safe and avoid danger and avoid poisoning when we are hunter-gatherers. They add immeasurably to our lives. Just imagine a world that was just in black and white. And the best colour in the whole world is the one that looks good on you, according to Coco Chanel. Okay. So I've got a question for you. Are oranges named oranges because oranges are orange, or is orange called orange because oranges are orange?
It'll take me a little while to understand the question, Leigh. That was absolutely fantastic, amazing, and a lot of the topics you touched on have some meaning for me because I'm interested in photography, digital photography. So many of the things are absolutely relevant to all of that. But for a very complex subject, I have to say you did more than scratch the surface. You certainly went into some detail, and I'm sure we're going to get some interesting questions. Should we look at the chat box first and deal with those? Barry, are you with us?
Yes, I am. I'm just getting it up on screen. Yeah, there are quite a few comments.
The first one I've got. The first question I think is from Reen van den Hondel. Is it true that people who are colourblind have more rod cells and consequently can see better in the dark?
I'm not aware of that at all. I don't think it's a real effect or situation.
Okay. And Tim
Or could
Gibbs.
it, sorry,
Oh,
can I just
come on,
comment?
Barry.
Or could it be that lacking colour perception, they learn to distinguish shades that the rest of us don't need to?
That's very probably true, because obviously, you know, we make all sorts of adjustments if you've got some sort of impairment. Then our brains are very plastic and can adapt to a situation. And it wouldn't surprise me at all that, I suppose you'd have to get by in life if you couldn't see colour, by being able to distinguish, you know, shades of grey, black and white and grey from one another very, very clearly. But I'm not aware of any increase in rod cells.
Okay, we've got Tim Gibbs in Torridge. I'm told I have very good peripheral vision, but
In the
red light test, he only sees the light as white on the periphery of his vision. Is that normal? So red goes to white on the periphery.
Right. Well, in the peripheral vision, there are very, very few cone cells at all. So in your peripheral vision, what you're actually seeing is light and dark, mainly, virtually no color perception. And in fact, I made the point earlier when we was talking about the fovea, where that gives you a really, really high resolution image. And as I say, it's about the size of your two thumbnails held at arm's length, and your brain fills in the rest. Literally. So you think you see a full detailed image in front of your face, or, you know, in front of you, but most of that is constructed by your brain. But in your peripheral vision, the main perception that is there is light and dark.
Okay, thank you, Leigh. We'll carry on with the chat box. I can see Chris Smith there with his hand up. If you just be patient a moment, Chris. Bill Stratford, what about zoltanite? Turkish gemstone changes colour according to ambient light? Question mark. Different under a light bulb or outside?
Yeah, well, that again is probably because outside there'll be a lot more UV.
Yeah.
And it's probably pleochroic.
Okay, and Max Barron says, how do we see brown, which also lacks a spectral wavelength?
Again, brown is one of those colours. It's a bit like black. It's because most of the light has actually been absorbed.
Yes.
And very little is actually transmitted into your eye.
Yeah, yeah. And Ian Coleman, is colour constancy responsible, or is it a purported left-hand and right-hand brain that makes us see that trainer differently? That's interesting, isn't it? So there's a hint that the brain behaves differently because some people are left-brained and some people right-brained.
I'm not aware of any difference to left and right side, but a colour constancy is something it's only really been studied in detail for the past decade or so, and as we saw with that dress, it can be incredibly surprising, and very much depending on the illumination and the adjustment that is made in the person's brain depending on the illumination, and we're all different, as that dress clearly illustrates.
Yeah, yeah. Okay, oranges are oranges. They were the first oranges, or no. That's from Ian. Tom Holloway, thinks that Salvador Dali used egg yolk for his yellows. Is there any truth in that? Do you know?
Well, I certainly know that egg and egg yolks have been used in painting and in art for many, many years to literally bind pigments to the canvas. So I wouldn't be surprised at all.
No, no, no. Okay, Barry, you want to take some?
Yes, I'm just going down. Oh, here we are. Here's one from Malcolm in Exeter. Funnily enough, Lee, you probably know him. We're seeing many old black and white films converted to colour. How do they actually know the original colour?
Well, I suspect, I mean, I would imagine they use a variety of different techniques. But I think, and these days, I'm absolutely sure they'll use a certain amount of computer processing to speed up the job. Because in the early days when they did that, they literally had to colour each frame. So you'll have an artist or a colorist would literally colour each object in each frame and then produce a new print.
Yeah. Max Barron has come back with, so how do colour printers construct brown for soil, etc.? Well, you told us that George Seurat inadvertently invented the colour printer, didn't he? With all those
Well,
dots.
he was the one that did the huge canvas with lots and lots and lots of different dots.
Yeah.
Again, it's just a combination, an appropriate combination of inks. I mean, color printers these days, especially inkjets, are incredible technology. I mean, the resolution that you can get is truly astounding. And to think that of firing out tiny, tiny little dots of ink with that accuracy and that resolution is quite incredible.
It is. It is indeed. Lots of thanks here, people. Really appreciating your talk and the PowerPoint. Excellent. How many photons per second do we process? Very roughly. Well, that's from a Peter Weston. Whether he was the inventor of the Western Master Exposure Picture, I don't know, but there is a good connection there.
How many photons do we per second? I would think it's in the many trillions.
Yeah, I have a recollection from my electro-optic days of black body radiator calculations, and it's something in the region of 10 to the power 24 for bright sunlight or something. But I know the dynamic range for which the human eye, over which the human eye will operate, is incredible.
Yeah, absolutely incredible.
And it's not just by virtue of the eye itself, it's the it's the iris. So you've got an instantaneous dynamic range of the eye, but you've also got the slower action of the eye's iris.
Yeah, but also if you go into a dark environment, say you go out in hopefully a place at night where there's very little light pollution. Over a period of about half an hour, your eyes will become what they call dark adapted.
Yeah.
And what's happening there is not only will your pupil open right out, but the visual purple, the rhodopsin in cells, will increase in your rod cells, and you'll get much better night vision because of that. But it takes 15 minutes to 30 minutes to get properly night adapted. And the way you can see this, and you can check your peripheral vision as well, is go out and look at pick up a particular constellation. Say, I don't know, the saucepan one, the what's it called, the Great Bear.
Yeah.
Just look at that, and just look at that, and don't move your eyes, but then shift your attention to your peripheral vision, and you'll start to see stars that you won't be able to see if you look directly at them.
Right.
And that's the rod cells picking out light and dark but if you focus, if you turn literally your fovea to it, if you turn your main attention to the star, it'll disappear.
Yeah. I have a related question while we're on the topic of dark adaptation, Leigh.
Yeah.
You recall all the old movies of naval wartime movies down in the old depths of the submarine there. Everybody's working with a very dim red light. Presumably this is about not spoiling their dark adaptation for when they want to look through the periscope at night, etc., etc. But we've already established that the eye is more sensitive in the green region.
Yeah.
So surely to enable the eye to see at all using red light requires a higher intensity, doesn't it, than it would in green light? So wouldn't a green light be more effective in retaining that dark adaptation?
No, I think they use the red light gives you just enough ability to function without causing the dark adaptation, the rhodopsin, to reduce in your eyes. So I'm guessing it's something along that. I mean, I go out in the garden sometimes with my dog. We live in fortunately, a very dark area, and I go out sometimes at night to walk the dog around the garden if we haven't been able to take him out in the evening.
Yeah.
And I've got some torches. I've got one here, in fact, and you can dial up the colour, so it's red, green, and blue. It also does UV as well. And I switch the red light on, and it means I can see where the dog is, but I can still see all the stars because my night vision's not affected.
Oh, but there's an experiment for you, Leigh. Try it on green one night. Go out on green and see if it works as well, or even better.
And I'm fairly sure the dog.
One more from the chat box. Not a colour question. What is astigmatism?
Astigmatism, right? Well, normally you focus, obviously, you bring the light to a focus on your retina through a combination of mainly the lens. But if your eye is not perfectly spherical, then if you go across the eye at a particular angle, the actual focus can change, because depending on the angle across your eye, you can have vision which is in focus in certain angles and out of focus in another. So what they have to do is to grind the lens to compensate for that.
Yeah.
So I've got particularly bad astigmatism in my left eye, and my lens is quite clearly asymmetric. So the focus, depending on the angle the light is coming into my eye, the correction is different because my focus is different.
Yeah, my daughter is an optometrist, and I suffer from astigmatism, and she puts it that my eyeball is not like a football; it's more like a rugby ball. And that is it, really. You've got a different focal length in the different axes.
Yeah.
Let's move over to Chris, shall we? Chris Smith, if you would unmute. Are you there, Chris? Yeah, well done.
Yes. Can you hear me?
Yeah.
Yes, I can. Yes.
Can you hear me? First of all, Leigh, can I say I was 35 years in an industrial surface coated, and colour was my life. That's the best presentation I've ever seen about colour ever. Thank you very much. That was wonderful. Absolutely.
That's a brilliant compliment. Thank you very much.
Couple of things. Just as a practical thing, I remember getting involved with some paint with a car company, Ford, red, and the way it was referred to, and we discovered what the problem was, it was referred to as metamerism. It was a red color, but under sodium streetlights, it went chocolate brown. Everybody thought they had defects on their paints. It was the original Ford, and I wonder if it was to do with they changed the pigment, and it was referred to as an effect called metamerism at the time. I don't know if you've heard of that.
Well, I must admit, I've not heard the term. All I can say is obviously I mean, if you're under sodium lights, you've got very, very narrow range of
Exactly,
wavelengths in terms of illumination. So it's bound to make I would think, pretty much all colours look very, very strange because you literally narrowing the illumination down to literally a couple of main wavelengths.
Yeah, yeah. We had to, the job I had, we had to take color tests every year, and we used another one. You mentioned one. The other, I seem to remember it was called the Oshigoi. It was similar to what I think you described, but the number of people who were colorblind, I had to deal with an industry who didn't understand it and gave us so many problems. One of the things we did to resolve it was we had what we call a black bag effect. We'd agree a color with somebody, like for instance with Panasonic or Sony or whatever, and you'd paint it on a panel, everybody would sign the back, it'd be sawn in half and then stuck in a black bag and hidden away. Whenever there was a dispute on color, they'd fetch and put these two samples together, see if the original. Well, I'm going back about 40 years ago now, but to give you some idea. But the number of times I've had problems with people who insisted the color was wrong, and we eventually had to prove to them that they were colorblind. It was amazing.
Yeah, I joined the pharmaceutical industry early in my career, and in order to get the job, I had to go through extensive colour blindness tests and pass them with flying colours. But my wife, I'm absolutely convinced now she's a tetrachromat, because the number of times we've had disputes over colours, especially where there's a subtle difference, you know, blues and turquoises and things like greens, she can see things I can't. I'm pretty convinced. So I'm fairly sure that she's got that extra cone cell.
Yeah, just on another thing is on the red-green color blindness. You know, people have a lot of problems with traffic lights, and it's been known.
Oh, yes.
You have to understand the sequence of them.
Yeah.
You can jump a red light, and I know of some people who have in fact done that and been seriously injured.
Okay, I've got a question here which I don't think we've addressed.
Absolutely brilliant presentation.
Thank you, thank you.
Yeah.
Why do some animals' eyes seem to light up at night when light is shone into them? That's an interesting one. I don't know the name of the membrane, but cats, dogs, and other animals have a membrane in their eye. What it does, it actually reflects some of the incident light back out, and that gives them better night vision.
Oh, okay. I just thought it was reflection off the retina.
No, it's a special membrane they have in their eye, which we don't have.
Oh, okay. That's interesting. Barry, you've got your
It's
hand
the
up.
mictitating membrane.
Oh, right.
Sorry, Carol
Okay.
Barrett. It's the mictitating membrane.
Right. Okay.
Aha, thank you. Okay, I'm going to butt in at this point. I'm looking at the clock. It's sort of 12:20. Lunchtime beckons. So as much as we could go on for a long time more, I do need to bring this to a close. Our next meeting is going to be taking place 4 weeks from today on Wednesday, the 12th of May. And we'd like to offer any of you the opportunity to make a presentation. Doesn't have to be a long one. 15 minutes is be fine. So if you'd like to volunteer, please let us know via the website. You think you've got the website address on the emails. You can email us using the Contact Us button, or you can post a comment in the chat box, and either way we'll get back to you. And even if you don't feel able to make a presentation, we'd still welcome your feedback after the meeting on any topic you like, and suggestions, and we'll take them all on board. I'm just about to finish, but I'm going to conclude with just another short film which might be of interest to any of you who are looking forward to flying off to the sun. So just bear with me while I share my screen.
I'm just going to mute everybody, Barry. So,
Okay, it doesn't take long.
oh, okay.
Here we
I won't
go.
bother then. I won't bother.
Don't bother, you don't need to.
This is your pilot speaking. My name is Adrian Oberhensli. I'm working from home today.
Right.
Well done, Barry.
So all I can say after that is be careful what you wish for. That's it. Thanks to Leigh again for entertaining us.
Thanks, Leigh.
No,
Very good. Very good.
Thanks again. Thanks, Steve, for helping me out, and thanks to all of you for taking part. So keep safe, and hope to see you all next time.